Hello, and welcome back to Deep Space Intelligence. I'm Liam, and if you're joining us for the first time, this is a channel where we take the universe seriously. We don't chase headlines, we follow the science, sit with the hard questions, and try to understand what the cosmos is actually telling us. Tonight, we are going to explore what might be the most unsettling question in all of astronomy, and it begins not in a laboratory, not in a telescope dome, but in a cafeteria at Los Alamos National Laboratory in the summer of 1950. Enrico Fermi, one of the most brilliant minds of the 20th century, was eating lunch with colleagues when the conversation turned, as conversations among physicists often do, to something genuinely strange. They had been discussing a cartoon that had appeared in a New Yorker magazine, joking about the mysterious disappearance of trash cans from New York City streets, with aliens as the culprits. The laughter faded, the meal continued, and then Fermi, seemingly out of nowhere, looked up from his food and asked a question that would echo through physics for the next 75 years. He asked simply, "Where is everybody?" He was not asking about the missing trash cans, he was asking about the universe. Given the sheer number of stars in the Milky Way, given the billions of years available for life to evolve, given how quickly our own civilization had developed, Fermi wanted to know why we had not seen any sign of extraterrestrial intelligence. Not a radio signal, not a megastructure, not a probe passing through our solar system, not even so much as a faint technological whisper from across the galaxy. Where, in all of that vastness, was everybody? That question is now formally known as the Fermi Paradox, and it is not merely a curiosity. It is one of the most consequential puzzles in all of science, because the answer, whichever answer turns out to be correct, will permanently change how we understand our place in the cosmos. And tonight, we're going to explore one of the most chilling possible answers. What if the universe is not silent because life is rare? What if it is silent because life is hiding? What if the great civilizations of this galaxy, older and far more powerful than our own, have spent thousands or millions of years making themselves as invisible as possible, because they know something we apparently do not? And what if we, with our radio transmissions and our golden records and our carefully encoded messages fired into the dark, are doing the one thing that every rational civilization eventually learns never to do? What if we are the only fools broadcasting our location? To understand why this idea is so scientifically serious and so deeply troubling, we need to start with some numbers. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. NASA's Kepler Space Telescope, before its mission ended in 2018, fundamentally changed our understanding of how common planetary systems are. The data from Kepler revealed that virtually every star in the galaxy has at least one planet orbiting it. Some stars have several. When astronomers process those results through careful statistical models, they find that there are probably tens of billions of Earth-sized planets sitting within the so-called habitable zones of their parent stars, that temperate orbital band where liquid water could exist on a surface. The Kepler data suggests somewhere between half a planet and 3 planets per stellar system sitting in that zone. Our galaxy, in other words, is absolutely saturated with potentially habitable real estate. Now, the Earth has been around for roughly 4.5 billion years. Life appeared on this planet within a relatively short time of its formation, suggesting that under the right conditions, biology gets started quickly. Intelligence, more complex and more contingent, arrived much later, but it did arrive. And here is the number that makes the Fermi Paradox so acute. The Milky Way is approximately 13 billion years old. That means there have been stars forming and cooling and nurturing planets for nearly 3 times as long as our Sun has even existed. If life arose even once on another world 1 billion years before Earth formed, that civilization has had 1 billion years of head start. If it arose 2 billion years before us, 2 billion years. Civilizations with that kind of temporal advantage over our species would be, by any reasonable measure, incomprehensibly advanced. They would make our current technology look like cave paintings, so why the silence? Why, in nearly 100 years of radio astronomy, have we detected nothing that convincingly says intelligent minds made this? Why, in our sky surveys, have we seen no megastructures, no rearranged star systems, no continent-scale engineering projects reshaping neighbouring worlds? Why, as we listen with our most sensitive instruments, does the cosmos return only the static of natural phenomena, the chirp of pulsars, the roar of colliding galaxies, the whisper of the cosmic microwave background, but nothing that sounds like a mind behind it. There are many proposed answers to this question, and we will walk through several of the most credible ones tonight. But before we do, I want to be honest with you about something. This channel works hard to present verified, scientifically grounded information, and everything we cover here is drawn from peer-reviewed research, data from missions like Kepler and the James Webb Space Telescope, and the serious scientific literature. That said, the Fermi Paradox touches on territory where science becomes genuinely speculative, where we are reasoning about things we have never observed, extrapolating from a sample size of one, meaning our own civilization. I always encourage you to read the original sources, cross-check the research for yourself, and form your own conclusions. That kind of intellectual independence is exactly what good science depends on, and it is what good thinking depends on too. Now, let us begin with what we actually know, because the picture is more interesting than most people realize. In 1960, a young radio astronomer named Frank Drake pointed the 85-foot radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani. He was listening for narrowband radio signals, the kind that a technological civilization would produce. He found nothing artificial. But the project, which he named Project Ozma, was the first serious, scientifically rigorous attempt to detect extraterrestrial intelligence using radio astronomy. Drake was undeterred. The same year, he developed what would become one of the most famous equations in the history of science. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy at any given moment. It multiplies together a chain of probabilities and rates: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of those where life actually arises, the fraction where that life becomes intelligent, the fraction where intelligent life develops detectable technology, and finally the average lifespan of a communicating civilization. When you run the numbers, even with conservative estimates, the equation tends to produce results suggesting we should not be alone. And yet, as decades of searching have made increasingly clear, we appear to be. This gap between what the Drake equation implies and what our instruments find is precisely the Fermi Paradox. The tension deepens further when you add what we have learned about exoplanets in recent decades. In 2020, a study published in the Astronomical Journal, drawing on data from the Kepler mission and led by researchers at NASA, calculated that there are likely around 300 million potentially habitable Earth-sized planets in our galaxy alone. 300 million in our galaxy alone. The universe contains somewhere in the range of 2 trillion galaxies. The arithmetic is staggering, and the silence is staggering right alongside it. As of recent tallies, the confirmed exoplanet count has passed 5,000, with thousands more candidates awaiting verification. We know that planet formation is not a rare accident. It is one of the most common outcomes of stellar physics. So let us consider the explanations. There are dozens of hypotheses, ranging from the prosaic to the profound, from the reassuring to the deeply alarming. Astronomers and philosophers of science have organized them into rough categories, and each carries different implications for what we should expect, and perhaps for how we should behave. The first category of explanation is simple. Life is extraordinarily rare, perhaps unique to Earth. This is sometimes called the rare Earth hypothesis, developed most prominently by paleontologist Peter Ward and astronomer Joe Brownlee in a book by that name published in 2000. Their argument is that Earth is not a typical planet. It has a large moon that stabilizes its axial tilt, preventing catastrophic climate swings that would otherwise make complex life almost impossible. It orbits in the galactic habitable zone, far enough from the dense, radiation-heavy galactic center to avoid constant sterilization by gamma-ray bursts and supernovae. It has plate tectonics, which recycles carbon and regulates temperature over geological timescales. It has Jupiter acting as a gravitational shield, deflecting many large asteroids that would otherwise bombard the inner solar system far more frequently. Layer all these coincidences on top of each other, Ward and Brownlee argue, and you begin to see how genuinely unusual Earth might be. Not just a planet with life, but a planet designed by an extraordinary sequence of chance to sustain complex life over the long timescales required for intelligence to evolve. If the rare Earth hypothesis is correct, the silence is simply a census result. There is nothing out there to find. The galaxy is full of lifeless rocks and toxic atmospheres, and worlds bombarded by cosmic radiation. We're not alone because others are hiding. We're alone because there are no others. But many scientists find this answer unsatisfying, partly because of the sheer scale of the universe, and partly because of what we continue to discover closer to home. Extremophile bacteria on Earth survive in conditions that would kill most life. The boiling water of hydrothermal vents, the hyperacidic interior of volcanic hot springs, the frozen deserts of Antarctica, even the vacuum-adjacent conditions at the edge of Earth's atmosphere. Tardigrades, sometimes called water bears, can survive in the vacuum of space, can withstand pressures 6 times greater than the deepest ocean trench, and can endure radiation levels that would kill any other known organism. Life, it seems, is stubborn. It finds a way into almost every available niche. The idea that these conditions for biology are uniquely present only on one small blue world in one average galaxy, among 2 trillion strikes, many researchers as cosmically implausible. The second major category of explanation is the Great Filter. This is a concept introduced by economist Robin Hanson in 1998, and it is both elegant and disturbing. The argument runs as follows. The universe is old, stars are common, planets are common, and yet we see no evidence of advanced civilizations. Therefore, somewhere along the path from simple chemistry to galaxy-spanning intelligence, there must be a step that almost no one survives. A barrier so improbable, so lethal, that the vast majority of potential civilizations never pass through it. This filter could lie in our past, in which case we have already crossed it, or it could lie in our future, in which case we are approaching it. If the filter is behind us, if the development of eukaryotic cells, or of multicellular life, or of something else in our deep biological past was the near impossible bottleneck, then we may well be the most advanced thing in the observable universe. We are the lucky survivors of a cosmic lottery. That is a somewhat comforting thought, if deeply lonely. If the filter is ahead of us, that is a different matter entirely. If something routinely destroys technological civilizations before they become visible across interstellar distances, if nuclear weapons, or runaway artificial intelligence, or ecological collapse, or some other existential hazard constitutes the filter, then the silence of the cosmos is not a sign of emptiness. It is a graveyard. Every silent point of light in the sky becomes a tombstone for a civilization that did not make it through. Nick Bostrom, the philosopher from Oxford's Future of Humanity Institute, made a famous and deliberately counterintuitive argument about this problem. He suggested that the discovery of any form of life elsewhere in the universe, even simple microbial life, would actually be deeply bad news for humanity, because it would imply that the filter was not in our past but in our future. If life is common enough to have arisen on Mars or on an ocean moon, then the bottleneck is not in the early stages of biology. It is somewhere further along the developmental path, which means we have not yet passed it. The Fermi Paradox, if you follow this reasoning to its logical conclusion, is not a puzzle to be solved with curiosity. It is a warning to be heeded with the same urgency we might bring to a catastrophe that has not yet happened. A 2024 study reviewed in Scientific Discussions suggested an additional wrinkle to this picture, that intelligent species might carry inherited behavioral patterns that are fundamentally incompatible with the long-term maintenance of technological civilization. In other words, evolution may wire minds in ways that work brilliantly for small tribal groups on a resource-rich planet, but catastrophically for species that develop nuclear weapons, industrial pollution, and artificial intelligence simultaneously. The capacity for raw intelligence and the capacity for long-term civilizational survival may not be the same thing, and may in fact be working against each other. But let us set aside for a moment both the rare earth hypothesis and the great filter, because there is a third category of explanation, and it sits at the very heart of tonight's exploration. What if the civilizations are out there, but they are quiet on purpose? What if the silence is not absence but strategy? This is the family of hypotheses that begins with the most famous of them all, the zoo hypothesis. Formally proposed by MIT radio astronomer John Ball in a 1973 paper, published in the journal Icarus, the zoo hypothesis suggests that advanced civilizations are aware of us, but have chosen, for whatever reason, not to make contact. They observe us from a distance, perhaps out of scientific curiosity, the way a biologist observes a colony of insects through glass, or perhaps out of an ethical commitment to non-interference, allowing less developed species to evolve without contamination from outside cultures. The silence on this reading is not emptiness, it is deliberate restraint. We are the animals in the zoo, they are outside the glass. The concept has an almost comfortable quality to it. The idea that we are being watched over, even in silence, even from a vast distance, suggests a universe with something like custodians. There is even a well-known science fiction precedent, the prime directive of the fictional Star Trek universe, which forbids the Federation from interfering with the development of civilizations that have not yet reached a certain technological threshold. Ball's hypothesis is essentially the serious scientific version of that concept. But the zoo hypothesis has a fundamental problem that many researchers have identified. It requires a near-perfect consensus among every civilization in the galaxy to maintain the non-contact policy. Every single advanced civilization, without exception, would need to agree not to break the silence. Not one maverick intelligence, not one rogue civilization, not one faction of any species with a different philosophical tradition would ever decide to break ranks and make contact. This kind of universal behavioral uniformity seems very difficult to justify on scientific grounds. Among the billions of potential civilizations that might have existed across galactic history, we would expect enormous variation in values, strategies, and choices, not a seamless galaxy-wide agreement maintained without deviation for millions of years. Researchers Ian Crawford and Dirk Schulze-Makusch made this point explicitly in a 2024 paper published in Nature Astronomy, arguing that, given this difficulty, the apparent absence of extraterrestrial technological civilizations is most plausibly explained by either their extreme rarity or by deliberate active concealment. They distinguished meaningfully between passive non-contact, in which civilizations simply do not broadcast, and active concealment, in which they deliberately mask their existence from detection. That second possibility is where the reasoning becomes genuinely strange, and, for many scientists, genuinely frightening. And this brings us to the idea that has captivated scientists, philosophers, and science fiction writers in roughly equal measure over the past decade. The idea that the universe is not simply quiet, but strategically dark. The theoretical framework now known as the dark forest hypothesis was most vividly articulated in a 2008 novel called The Dark Forest by Chinese science fiction author Liu Cixin, the second volume of his celebrated three-body problem trilogy. But the underlying logic predates Liu's work and has roots in serious scientific and philosophical literature going back at least to David Brin's 1983 survey of Fermi Paradox solutions in the academic journal Acta Astronautica. The image Liu created was, however, so precise and haunting that it has become the dominant frame through which this class of explanations is now widely discussed. In Liu's vision, the universe is a dark forest. Every civilization is an armed hunter, moving through that forest in total silence, stepping carefully, making no sound, revealing no light. Not because there is nothing else in the forest, precisely because there is everything else in the forest. Because any sound, any light, any signal of existence immediately draws the attention of other hunters, and in this forest, contact between hunters almost always ends the same way. The logic of the dark forest rests on two foundational assumptions, both of which Liu carefully argued and both of which have been seriously examined by real scientists. The first assumption is that all life, by the nature of the evolutionary process, fundamentally requires resources, whether energy, matter, space, time, or some combination of all of these. Resources in the universe are finite, even if the universe itself is vast. The second assumption follows from the first, that civilizations separated by interstellar distances cannot fully verify the intentions of other civilizations. You cannot truly know whether another intelligence is benevolent. You cannot be certain they will remain benevolent even if they appear to be now. You cannot be sure that what looks like a peaceful contact is not the preliminary stage of an extinction event, a scout surveying before the main force arrives. Given these two conditions, resource competition and irreducible uncertainty about intentions, the rational strategy for any civilization that wants to survive long enough to become powerful is to eliminate potential threats before those threats can grow large enough to eliminate you. And the most dangerous moment in that calculus is the moment when another civilization first reveals itself, because that is the moment when you know exactly where it is, before it knows precisely how strong you are. In the dark forest, being seen first is fatal, silence is survival, and the civilizations we observe today, through their silence, are the ones that understood this lesson early enough. The universe, on this reading, is not a silent library or a lonely void. It is a battlefield in which the combatants have evolved, across billions of years of natural and technological selection, to be absolutely invisible. Every civilization that ever made itself conspicuously known has been destroyed or suppressed. Every civilization that survives has learned to hide with ruthless discipline. The silence is not the absence of life. It is the sound of 10,000 civilizations holding their breath. Now, I want to be careful here. The dark forest hypothesis is intellectually striking, but it is not a proven theory. It is, at present, one of several competing explanations for the Fermi Paradox, and it rests on assumptions about the psychology and strategy of alien intelligences that we cannot by definition verify. As a 2024 comparative analysis from researchers evaluating 15 major Fermi Paradox hypotheses noted, the dark forest theory ranked fourth among proposed solutions when scored across criteria including logical consistency, empirical support, mathematical rigor, and testability. The hypothesis that scored highest in that analysis, the estivation hypothesis, which proposes that advanced civilizations have entered a state of dormancy and are waiting for the universe to cool sufficiently to run more thermodynamically efficient computations, is in some respects even stranger than the dark forest. The point is not that the dark forest is the definitive answer. The point is that it is taken seriously by serious people, and that its internal logic is genuinely difficult to dismiss. The astrophysicist and philosopher of science Tony Milligan, a research fellow at King's College London working on the Cosmological Visionaries project, has argued that the dark forest solution is ultimately unconvincing precisely because it requires so many behavioral assumptions about alien minds. He suggests the silence is equally likely to indicate that other civilizations are simply too distant, or that our listening methods are fundamentally misaligned with how advanced intelligences actually communicate, or that there genuinely is nothing to find. That is a fair and properly skeptical position, but it does not eliminate the possibility. It simply reminds us that we are working in near total darkness, reasoning about entities whose existence we have not even confirmed. What we can say with some confidence is this: if the dark forest hypothesis is even partially correct, the behavior of our own civilization over the past century has been, from a strategic standpoint, extraordinary. Because we have not been hiding. We have been shouting. It started, in a sense, before we even meant it to. The moment we began broadcasting radio signals, we began leaking electromagnetic radiation into space at the speed of light. Our first significant radio transmissions, going back to the early 20th century, have been expanding outward from Earth in a sphere roughly 100 light-years in radius. This electromagnetic bubble contains our old television signals, our radar pulses from wartime and peacetime defense networks, our satellite uplinks, our telecommunications traffic, all of it radiating away in every direction, a growing announcement to anyone with the right equipment. There is a technological civilization here, and here is precisely where to find it. By the early 1970s, we decided to be more deliberate about it. In 1972 and 1973, NASA launched Pioneer 10 and Pioneer 11, two spacecraft each carrying gold anodized aluminum plaques designed by Carl Sagan and Frank Drake. Those plaques depicted a man and a woman, a diagram of our solar system with the origin planet marked, a representation of the hyperfine transition of hydrogen, a kind of universal unit of measurement, and a pulsar map indicating our location relative to 14 known pulsars in the galaxy. The spacecraft were designed to eventually leave the solar system entirely, carrying those plaques into interstellar space for potentially billions of years. As of this recording, Pioneer 10 has travelled more than 8 billion miles from Earth and is moving outward at approximately 27,000 miles per hour. It is carrying our address. Then, in 1974, the Arecibo radio telescope in Puerto Rico, under the direction of Frank Drake and Carl Sagan, fired a radio message toward the globular cluster Messier 13, a dense congregation of roughly 300,000 stars located approximately 25,000 light-years from Earth. The message was encoded in binary arithmetic, depicting human DNA, our solar system, a schematic representation of the human form, and the Arecibo telescope itself. It was transmitted at a focused power equivalent to 20 trillion watts, if radiated in all directions equally, a signal that, in theory, could be received by a telescope the size of Arecibo anywhere in the galaxy. The message will not reach Messier 13 for approximately 25,000 years, and a reply, if one were ever sent, would take another 25,000 years to return. But the point, at the time, was not practical communication. It was demonstration. Proof that we had the capability to reach across the galaxy with our voices. In 1977, NASA launched the Voyager probes. Each carried a golden record, a 12-inch gold-plated copper disc containing sounds and images selected by a committee chaired by Carl Sagan to represent the diversity of life and culture on Earth. The records included greetings in 55 languages, music from dozens of human cultures, ranging from Beethoven to Chuck Berry to Azerbaijani bagpipes, the sounds of rain and surf and wind and thunder, photographs of mathematics and anatomy and cities and children, and the brainwave recording of Anne Druyan, who was, at the time of recording, thinking about her love for Carl Sagan. The records also included a pulsar map pointing with considerable precision to the location of our solar system in the galaxy. A care was taken, as the committee noted, to include information not only about humanity, but about all life on Earth, making the record as much a document of the living biosphere as of our civilization. Voyager 1 crossed into interstellar space on August 25, 2012, becoming the first human-made object to leave the solar system. Voyager 2 followed on November 5, 2018. By 2022, Voyager 1 was more than 14 billion miles from Earth, continuing outward into the darkness, carrying our music and our faces and our exact galactic coordinates on a disk designed to survive for billions of years. Gold is extraordinarily non-reactive. If nothing destroys the probe physically, the record could theoretically outlast the Earth itself. There is something undeniably beautiful about this. The desire to communicate, to reach out into the dark and say, "We are here and we are alive and we have made beautiful things," is one of the most deeply human impulses there is. Carl Sagan, who understood this better than almost anyone, knew that the probability of the golden record ever being found by another intelligence was vanishingly small. But he believed that even a small chance of connection was worth taking, and that the act of creating the record was valuable in itself, regardless of who might eventually find it. He understood too that the record told us something important about ourselves in the making of it, about what we chose to represent, about what we considered worth remembering. But Sagan also understood the risks. In a 1994 interview, he was asked about the wisdom of broadcasting our presence. He said that if we had never sent any signals, perhaps it would be sensible not to start, but that we had already done so, and the information was already out there. Stephen Hawking was more direct. In a 2010 series for the Discovery Channel, he said that attempting to contact extraterrestrial civilizations was, in his view, too risky. He compared the likely outcome to the meeting of Native Americans and Christopher Columbus, and noted bluntly that that encounter did not go well for the Native Americans. Hawking's point was not that aliens are necessarily malevolent in intent. It was that when civilizations with vastly different levels of technological development make contact, the dynamics tend to be catastrophic for the less developed party, regardless of what either side intends. This concern has generated a genuine and ongoing scientific controversy, one that continues to divide researchers in the field of SETI and METI. SETI, as most of you know, is the search for extraterrestrial intelligence, the passive listening side of the enterprise. METI stands for Messaging to Extraterrestrial Intelligence, the active side, deliberately transmitting signals toward potential recipients. The debate between advocates of METI and their critics is not a fringe conversation. It involves serious scientists and has been the subject of peer-reviewed papers in journals including Acta Astronautica and the International Journal of Astrobiology, and it touches on some of the deepest questions about risk, responsibility, and what it means to act on behalf of the human species. The critics of active messaging, including researchers like John Billingham and James Benford, have argued in detail for what they call a global moratorium on active transmissions. Their 2010 paper analysed both the theoretical risks and the practical challenges of METI, concluding that the potential downside of attracting an unfriendly, or simply indifferent but enormously more powerful civilization is severe enough that humanity should not proceed without international consensus. That consensus, as of this recording, does not exist. There is no international body with the legal authority to regulate what gets sent into space from Earth, no treaty governing METI, no mechanism by which the global population could collectively decide whether to broadcast our existence to the universe. Individual researchers and organizations can simply decide on their own initiative to fire signals into the cosmos. The central problem, as one review of METI ethics summarized with stark directness, is that there is no one with the mandate or the authority to make this decision on behalf of humanity. The advocates of METI counter that this fear is misplaced. They argue that Earth's electromagnetic leakage has already made us detectable, that the electromagnetic sphere radiating from our planet has been expanding at the speed of light for a century, and that any civilization advanced enough to pose a threat is probably also advanced enough to have noticed us already. They also argue that the potential benefits of contact are transformative, that knowledge and perspective gained from interaction with another intelligence would dwarf the risks. Jonathan Jiang, an astrophysicist at NASA's Jet Propulsion Laboratory, has been among those who have advocated for more deliberate and thoughtful interstellar messaging. In 2022, Jiang and colleagues published a proposal for an updated transmission scheme they called the Beacon in the Galaxy, a modernized interstellar message designed to take advantage of more powerful contemporary radio facilities and to include a more sophisticated and comprehensive description of human civilization and biology. The proposal remains just that, a proposal, not a funded or executed project as of this recording. But it represents a serious scientific case for active outreach, at a time when that case is deeply contested. And here, I think it is worth pausing for a moment. Because we're talking about decisions that affect every human being alive, and every human being who will ever be born. And the people making those decisions, or not making them, are a relatively small community of scientists, engineers, and enthusiasts. This is one of those rare situations where the gap between the magnitude of the consequences and the breadth of the decision-making process is almost comically large. I encourage you to think critically about this. Look into the METI debate yourself. Read the original papers. Look at the arguments from both sides. Form your own view. Because this is not just a scientific question. It is a question about who gets to speak for humanity. The METI debate is not merely abstract, because there is a deeper question lurking beneath it. A question that the dark forest hypothesis puts in the sharpest possible terms. In a universe we do not fully understand, populated by intelligences we have never met, what is the rational strategy? Is it to call out, hoping to find a friend, or even just a conversation partner? Or is it to stay quiet in case something is listening that we would not want to find us? And here is where the science becomes genuinely strange. Because there is evidence, not proof, but evidence, that we have not been entirely alone in our electromagnetic neighborhood. Evidence that something, at least once, sent a signal that looked different from anything natural astronomy had ever produced. On the night of August 15, 1977, Ohio State University's Big Ear radio telescope was scanning the sky, as it did routinely, listening for narrowband radio signals near the hydrogen line frequency of approximately 1,420 MHz. This is the frequency at which neutral hydrogen atoms naturally emit radiation, and astrobiologists have long considered it the most likely candidate for interstellar communication, a universal landmark in the electromagnetic spectrum, the kind of frequency any civilization studying basic physics would recognize, and any intelligence seeking contact would logically use. Astronomer Jerry Ehman was reviewing the printout of recorded data a few days later when he found a sequence of characters that stopped him completely. The signal had appeared at almost exactly 1,420 MHz. It was 30 times stronger than the background noise of the sky, an extraordinary amplitude. It had lasted 72 seconds, the precise duration expected for a signal coming from a fixed point in space as the rotating Earth carried the telescope past it. It appeared to originate from the direction of the Sagittarius constellation, and it had never in any scan of that region before appeared. Ehman circled the data in red ink and wrote a single word in the margin of the printout. Wow! The wow! Signal, as it immediately became known to the broader scientific community, remains one of the most discussed anomalies in the history of the search for extraterrestrial intelligence. For decades, scientists struggled to find a natural explanation that accounted for all its properties. Terrestrial interference was ruled out early. Passing satellites were investigated and excluded. The signal had never appeared before and never appeared again, despite dozens of deliberate follow-up attempts to observe the same region of sky. The director of Big Ear at the time, John Krause, wrote in a letter to Carl Sagan that the WOW signal was, in his professional judgment, highly suggestive of extraterrestrial intelligent origin. For nearly 40 years, that assessment stood unchallenged, not because scientists believed it was alien, but because no one could definitively prove otherwise. More recently, in 2024, a team led by Abel Mendez at the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo published new analysis under what they called the Arecibo WOW project, an initiative established to re-examine unexplained radio signals using modern scientific methodologies. Their analysis proposed a natural explanation, that the signal may have been a rare form of astronomical massive flare, caused by a powerful transient cosmic event such as a magnetar flare or a soft gamma repeater interacting with a cold cloud of interstellar hydrogen. Under very specific conditions of geometric alignment and energy transfer, the researchers argued, such an event could cause a hydrogen cloud to emit a brief but intensely powerful burst at exactly the hydrogen line frequency. This process, known as stimulated emission, is extremely rare and would explain why the signal was never detected again. Subsequent work in 2025 refined this hypothesis further, suggesting the original signal may have been even stronger than originally estimated, lending additional weight to the natural phenomenon interpretation. So the WOW signal is probably not an alien transmission. The scientific consensus is shifting cautiously but steadily toward a natural astrophysical explanation. But notice what the resolution of this mystery teaches us. The signal was so narrow-band, so precisely tuned to the hydrogen line, so apparently artificial in its characteristics, that for nearly 5 decades it fooled some of the best radio astronomers in the world. Its apparent artificiality was not a product of careless observation or wishful thinking. It genuinely had, by every standard we had developed for evaluating potential technosignatures, every quality that an intelligent signal would be expected to have. And it was not. Or at least it almost certainly was not. That is either reassuring or deeply unsettling, depending on how you look at it. Reassuring because it demonstrates that our detection methods are sensitive enough to catch rare natural phenomena masquerading as the artificial signals. Unsettling because it is a vivid reminder of how difficult this search actually is, how hard it is to distinguish a deliberate transmission from a naturally occurring one, and how much we might be missing in the noise. Which brings us back to the central question. If civilizations are hiding, if they have learned, over thousands of years of technological development and perhaps painful historical encounters, never to make themselves conspicuous, then the silence we observe is exactly what we would expect. A universe full of intelligent life, all of it invisible, all of it listening, none of it willing to be the first to speak. And somewhere in that silence, a small, young, enthusiastic civilization on a rocky planet around an unremarkable star, firing radio waves in every direction, sending probes with maps to its home address out into the dark, and asking, louder and louder, is anyone there? We have been searching for other civilizations for over 60 years now. The Breakthrough Listen initiative, launched in 2015 with a 10-year, $100 million commitment backed by entrepreneur Yuri Milner, is currently the most comprehensive and systematically designed search for extraterrestrial intelligence in human history. It uses a global network of leading radio and optical telescopes, including the Robert C. Byrd Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, supported by custom digital instrumentation and advanced data analysis pipelines. By 2020, Breakthrough Listen had released nearly 2 petabytes of data from the most comprehensive radio survey yet of the plane of the Milky Way galaxy and the region around its central black hole, making the data publicly available for anyone to search. The results, as of this recording, include precisely 0 confirmed detections of an artificial signal from beyond Earth. Breakthrough Listen's null results represent the most stringent upper limits ever placed on the prevalence of high-power artificial transmitters in the universe. Their surveys have set constraints that are vastly superior to all previous efforts in terms of spectral resolution, temporal resolution, sensitivity, and the sheer number of stars examined. In 2023, a team at Cornell University and the SETI Institute, working in collaboration with Breakthrough Listen, conducted what was described as the first comprehensive search for periodic signals from the galactic center under the project name BLIPSS, the Breakthrough Listen investigation for periodic spectral signals. They found no confirmed technosignatures from the galactic core. A 2024 study by Breakthrough Listen researchers, examining 97 nearby galaxies for artificial radio transmissions over 5 years of observation time, similarly found nothing that could not be explained by natural astrophysical processes. The universe is not merely quiet to casual inspection. It is quiet to the most sustained, most sensitive, most scientifically rigorous listening campaign in human history. And yet, the logic of the dark forest suggests that this is precisely what we should expect, if it is right. Civilizations advanced enough to be detectable would also be advanced enough to control their electromagnetic footprint. A civilization at what the Soviet astrophysicist Nikolai Kardashev called Type 2 on his scale of civilization development, meaning one that has learned to harness the full energy output of its parent star, would also have the engineering capacity to direct its communications with surgical precision, rather than broadcasting energy wastefully in all directions. Such a civilization would not leak. It would not accidentally announce itself. Every photon would be purposeful. Consider what it means to build a Dyson sphere, the theoretical megastructure proposed by physicist Freeman Dyson in 1960. A Type 2 civilization, by Kardashev's definition, commands an energy budget equal to the total output of its star, on the order of 4 times 10 to the 26th watts, or about 400 trillion watts. A Dyson sphere built around our own Sun would have a surface area roughly 600 million times greater than the surface area of Earth. The engineering challenges are staggering, but for a civilization with billions of years of development time, the physics are not forbidden. And the signature of such a structure, Dyson himself pointed out, would be a star that radiates in the infrared spectrum at temperatures corresponding to room temperature surfaces, because the shell would absorb starlight and re-emit it as waste heat. Astronomers have looked for these signatures. They have found candidates, including Tabby's star, which exhibited extraordinary dimming events of up to 22% when examined by the Kepler Space Telescope. But follow-up observations, including radio surveys by Breakthrough Listen, found no artificial emissions from that system, and photometric analysis eventually attributed the dimming to circumstellar dust. Tabby's star is not a Dyson sphere in construction. It is a dust-obscured star with unusual geometry. But the fact that we found no evidence of a megastructure does not mean that a civilization sophisticated enough to build one could not also be sophisticated enough to hide it. A Type 3 civilization, one commanding the energy resources of an entire galaxy, as Kardashev imagined it, would have technology so far beyond our own that we might not even recognize its signatures as technological at all. Our instruments are calibrated to find things that look like us. What if the most advanced civilizations have long since evolved beyond the kind of physics we currently understand? What if they communicate through modalities we have not conceived of, using methods that leave no electromagnetic trace we would know to search for? This is not an idle thought experiment. It is a recognized fundamental limitation of all current SETI methodology. Researchers in the field acknowledge it openly and regularly. We are searching for keys under the lamppost, as the saying goes, because that is where the light is. Our searches are constrained by our own technological and conceptual horizon. We cannot search for what we cannot imagine, and we cannot imagine what we have never encountered. The question of whether to communicate is further complicated by a concept that cosmologists and philosophers of mind have increasingly begun to examine together: the problem of interstellar time. We tend to imagine civilizations as static things, as persistent entities with consistent goals and values that we could potentially negotiate with or appeal to. But a civilization that has existed for 1 billion years is not the same civilization it was 1 million years ago, any more than we are the same species that built the first stone tools 2.5 million years before the present. Values change, philosophies change, technologies change. Biological substrates change. A civilization that was benevolent and curious 100 million years ago may have transformed, gradually or catastrophically, into something entirely different. The entity that might receive our Voyager Golden Records or detect our radio transmissions may bear no meaningful relationship in values or cognition to the civilization that sent its first tentative signals across the cosmos millions of years earlier. This temporal dimension adds yet another layer of uncertainty to the risk calculations around broadcasting our presence. Even if we could determine that a particular civilization was benevolent right now, we cannot know what it might become. and the lag time in any interstellar exchange is measured in decades, centuries, or millennia, depending on distance. By the time any response to our signals could possibly arrive, our own civilization will have changed in ways we cannot begin to predict. The conversation, if it ever happened, would not be between the civilization that sent the message and the civilization that received it. It would be between strangers separated by not only space but deep time. There is another hypothesis that deserves attention here, one that sits between the zoo hypothesis and the dark forest and shares something of each. It is sometimes called the interdict scenario, or in more technical literature the berserker hypothesis, named after Fred Saberhagen's science fiction series. The core idea is that some ancient civilization, or network of civilizations, long ago concluded that the safest policy for the long-term stability of the cosmos was to prevent the emergence of any additional galaxy-spanning power. Rather than remaining passive observers, these ancient intelligences seeded the galaxy with self-replicating autonomous machines, probes that travel from star system to star system, monitor for the emergence of technological intelligence, and take action to prevent any young civilization from crossing the threshold of detectability or interstellar capability. The concept was formalized in scientific literature as early as 1983 by the astronomer David Brin, and it remains a recognized, if highly speculative, solution to the Fermi Paradox. The disturbing elegance of the berserker scenario is this: once such a system has been deployed, it does not require the continuing involvement of its creators. The probes replicate, the network expands, the galactic policing operates autonomously across billions of years. The original civilization may long since have gone extinct, or evolved into something unrecognizable, and yet the machines they built continue their ancient mission, maintaining the silence of the forest by eliminating anything that breaks it. What is particularly unsettling about this possibility is the implications for our own search. We have looked for radio signals from other civilizations. We have searched for megastructures around nearby stars. We have scanned the skies for infrared anomalies that might indicate technological activity. We have not searched, at any serious level, for artifacts in our own solar system. The Lagrange points, those gravitationally stable regions of space where objects can orbit in a fixed relationship with the Earth and the Sun, would be natural hiding places for small passive monitoring devices. They have been cursorily examined but not surveyed with anything approaching systematic thoroughness. The outer solar system, vast and cold and largely unexplored, contains billions of objects in the Kuiper belt and the hypothesized Oort cloud, any one of which could conceal an artifact of negligible size but significant capability. We have not looked there. Not really. We have barely begun to look. The James Webb Space Telescope, the most powerful astronomical observatory ever placed in operation, has opened extraordinary new windows on the universe since its commissioning in 2022. Its infrared sensitivity allows it to peer into the atmospheres of exoplanets as they transit their parent stars, searching for molecules that might indicate biological or technological activity, what scientists call biosignatures and technosignatures. Initial results from Webb have been more cautious than some hoped. No confirmed biosignatures yet, though several intriguing candidates exist and the search is ongoing. The telescope's primary mission is the distant universe, not the search for life per se. But its capability represents a genuine leap in our ability to characterize the atmospheric chemistry of worlds around other stars, and in the coming decades, it may help us determine whether some of those worlds host chemistry that simple physics and geology alone cannot explain. What Webb cannot do is listen for radio signals. Radio telescopes remain, for the time being, our best hope for detecting deliberate transmissions, if any are being sent. And the infrastructure for that search is not standing still. The 500-meter aperture spherical telescope in China, known as FAST and completed in 2020, is currently the world's largest filled aperture radio telescope. With a collecting area roughly twice that of the former Arecibo Observatory, whose main platform collapsed in December 2020 after decades of operation, FAST has significantly expanded humanity's radio listening capacity. The Chinese Academy of Sciences has indicated that FAST will participate in SETI research, and in 2022, reports emerged that the telescope had identified some candidate signals of interest, though these were subsequently determined to be the result of radio frequency interference from human technology on Earth. The story of those candidate signals, briefly reported and then quietly retracted once terrestrial interference was identified as the source, illustrates one of the persistent practical challenges in CT. The Earth is an extraordinarily noisy place, electromagnetically speaking. Our own technology generates radio frequency interference across virtually the entire spectrum that SETI researchers want to search. Every mobile phone, every satellite, every radar installation, every digital device produces electromagnetic noise that can mimic, to varying degrees, the signatures we're looking for in the sky. The task of separating genuinely extraterrestrial signals from this terrestrial background is among the most technically demanding in observational astronomy. The situation is about to become considerably more challenging. The proliferation of low Earth orbit satellite constellations, including SpaceX's Starlink network, which had deployed several thousand satellites as of early 2024, with plans for tens of thousands more, is generating electromagnetic noise across a broad spectrum of radio frequencies. Astronomers, including those involved in SETI research, have raised serious concerns about the long-term impact of these constellations on radio astronomy. Light pollution from reflective satellites has already affected optical observatories. Radio frequency interference from satellite downlinks and crosslinks may, in coming years, substantially narrow the frequency windows available for quiet radio observation. The very infrastructure of our expanding technological civilization is making it harder to listen for signs of other civilizations. There is something philosophically resonant about that particular difficulty. In our rush to connect every corner of the Earth with high-speed communications, we are inadvertently jamming ourselves, wrapping our planet in a shell of electromagnetic noise that makes it harder to hear anything coming from outside. We are becoming louder to the universe at the same time as we are becoming less able to listen to it. Whether that is ironic or simply the expected behavior of a young, resource-hungry civilization that has not yet learned to be careful, I leave to your own interpretation. I want to take a moment here, as we have now covered a great deal of material, to be transparent about the state of knowledge in this area. Everything we have discussed tonight, the Fermi Paradox, the Great Filter, the zoo hypothesis, the dark forest, the berserker scenario, all of it represents serious scientific and philosophical thinking by credible researchers at credible institutions. But none of it is settled. None of it is proven. We are reasoning about phenomena we have never observed, drawing inferences from an absence of evidence, and extrapolating from a single data point, which is our own civilization. The honest scientific position is that we do not know why the universe is silent. We do not know whether life is common or rare. We do not know whether advanced civilizations exist. And we do not know whether broadcasting our presence is wisdom or recklessness. I encourage you, as I always do on this channel, to sit with that uncertainty, to investigate these questions yourself, to read the original papers and the critical responses, and to resist the temptation to find simple comfort in any single explanation. The universe almost certainly does not resolve itself into a neat answer just because we want one. What we do know is this: the question matters. If there are other civilizations, understanding their silence or their presence or their intentions has consequences that dwarf virtually any other scientific or geopolitical question facing our species. And if there are no other civilizations, if we are truly alone in this ancient and enormous universe, that knowledge carries its own profound weight. Either way, how we approach the search, what we transmit and what we listen for and what we assume about the nature of minds that are not ours, reflects something fundamental about who we are and what kind of civilization we intend to become. The Drake equation, which Frank Drake wrote on a blackboard for a small group of scientists gathered in Greenbank, West Virginia, in November 1961 for the first SETI conference, was never intended to give a definitive answer to how many civilizations exist. Drake himself said so. The equation was a framework for thinking, a way of breaking a single enormous question into a series of smaller, more tractable ones. Some of those smaller questions we have since answered with considerable precision. We know, thanks to Kepler and TESS and the extraordinary work of planet-hunting astronomers, that planetary systems are common. We know that habitable zone planets are common. We have begun to learn, through the spectroscopic analysis enabled by telescopes like Webb, how to look at the atmospheres of those planets. The first variables in Drake's equation are now reasonably well constrained. The later variables remain almost entirely mysterious. How often does chemistry become biology? We genuinely do not know. It happened once, here, under conditions we're still working to understand. How often does biology become intelligence? We have one example. How long do technological civilizations typically last? We have been technological, in any meaningful sense, for perhaps 10,000 years, and broadcasting into space for 100. We have no reference class. Every estimate of the longevity of communicating civilizations is, at present, a guess dressed in mathematical clothing, and it is in those unknown terms that the full weight of the Fermi Paradox resides. If civilizations are common and long-lived, the silence is deafening. If civilizations are common but short-lived, the silence is a graveyard. If civilizations are rare but hiding, the silence is a strategy. And if we are alone, the silence is simply the sound of one voice speaking into a room it thought was full. The night sky, seen from a place far from city lights, is one of the most humbling things a human being can experience. Somewhere in the range of 9,000 stars are visible to the naked eye under ideal conditions, all of them within a few thousand light-years of Earth, all of them part of the same small corner of one ordinary galaxy. The Milky Way itself, stretching in its faint arc across the darkness, contains somewhere between 100 billion and 400 billion of them, and the Milky Way is one galaxy among roughly 2 trillion in the observable universe. To look at that sky and imagine that in all of it, across all of that space and all of that time, only this one small world has ever produced a mind capable of looking back. That is a thought that either fills you with wonder or with loneliness, and possibly with both simultaneously. To look at that same sky and imagine that it is full of minds, all of them watching, none of them speaking, all of them calculating, all of them hiding, waiting to see what the newest, noisiest arrival in the forest will do next. That is a thought of a different kind entirely. And so we arrive at a place that is both scientifically honest and genuinely humbling. We have a universe that should, by any statistical measure, be full of intelligence. We have instruments that are the best we have ever built, listening harder than we have ever listened. We have found nothing. And we have a hypothesis, growing in seriousness among those who study these questions, that the silence is not vacancy but discipline, not emptiness but strategy, that the universe is full of life that learned, long ago, that the most important thing a civilization can do is nothing at all. If that is true, then what does it say about us still sending our golden records into the dark, still hoping something out there will write back? Are we brave? Are we naive? Are we, as the title of this documentary suggests, simply the only fools in the forest who have not yet learned to be afraid? And so we arrive at a place that is both scientifically honest and genuinely humbling. We have a universe that should, by any statistical measure, be full of intelligence. We have instruments that are the best we have ever built, listening harder than we have ever listened. We have found nothing convincingly artificial. And we have a hypothesis, growing in seriousness among those who study these questions for a living, that the silence is not vacancy but discipline, not emptiness but strategy, that the universe is full of life that learned, long ago, that the most important thing a civilization can do is nothing at all. If that is true, then what does it say about us, still sending our golden records into the dark, still hoping something out there will write back? Are we brave? Are we naive? Are we, as the title of this documentary suggests, simply the only fools in the forest who have not yet learned to be afraid? To sit with that question honestly, we need to think carefully about what a truly advanced civilization might actually look like. Because one of the most common errors in thinking about the Fermi Paradox is the assumption that other civilizations, if they exist, would necessarily be recognizable to us. That they would use radio waves to communicate because we use radio waves. That they would build physical structures we could see because we build physical structures. That they would need planets the way we need planets, or consume energy in ways that leave signatures we would know to search for. This assumption is, when examined carefully, extraordinarily parochial. It is the assumption that the universe tends to produce minds like ours, using methods like ours, pursuing goals like ours, and there is very little reason to believe that is true. The evolutionary trajectory of intelligence on Earth has been shaped by an almost incomprehensible series of specific accidents. The mass extinction that killed the non-avian dinosaurs 66 million years ago cleared ecological space for the mammalian radiation that eventually produced primates. A different impact trajectory, a slightly different atmospheric composition at the moment of the asteroid's arrival, a different sequence of climate fluctuations over the Paleogene, and intelligence might have taken a completely different form on Earth, or never emerged at all from the particular biological lineage we represent. The intelligence that exists on other worlds if it exists, has been shaped by entirely different contingencies, entirely different physical environments, entirely different evolutionary pressures. There is no compelling reason to believe it would converge on anything resembling us. And if that is true of biology, it is even more true of technology. Civilizations a million years older than ours have not simply had more time to build better versions of what we have. They have had time to discover physical principles we do not yet know exist. They have had time to develop capabilities that would look, to our instruments and our understanding, indistinguishable from natural phenomena. The line between sufficiently advanced technology and nature itself may become genuinely impossible to draw from the outside. This is not merely a philosophical point, it has real implications for how we interpret the silence. The physicist Michio Kaku has made a version of this argument in public lectures and in his writing. He notes that to an ant colony, human civilization is essentially invisible. The ants live in the soil, build their tunnels, gather their food, manage their colony with extraordinary collective intelligence for their kind. But a human highway built directly across their habitat would not register as a structure to them. It would register as a strange, smooth, hot surface with periodic lethal vibrations. The civilization that built it would be, in any meaningful sense, beyond their comprehension. Kaku suggests that our position relative to a Type 3 civilization may be broadly analogous. If that analogy has any force, then the absence of detected signals does not necessarily indicate an absence of civilization. It may indicate a profound absence of comprehension on our part. We may be the ants staring at the highway, mistaking the pavement for a natural rock formation and moving on. But let us hold that thought for a moment, because there is another possibility that many researchers have come to take very seriously over the past 2 decades, a possibility that sits at the intersection of evolutionary biology, artificial intelligence, and the deep logic of technological development. The possibility that advanced civilizations do not spread across the stars because they do not want to, not because of fear, not because of the dark forest, not because the Great Filter has eliminated them, but because at a certain point in technological development, the external universe simply stops being interesting enough to justify the effort. This is the core of what John Smart, a futurist and researcher in evolutionary development, proposed under the name the Transcension Hypothesis in a 2012 paper. The idea, stated plainly, is that sufficiently advanced civilizations do not expand outward into the galaxy. They expand inward, into inner space rather than outer space, into increasingly miniaturized, densely packed computational and experiential environments of their own creation. Rather than colonizing star systems, they build and inhabit virtual realities of incomprehensible richness. Rather than sending ships across the light years, they run mines at speeds and densities that make the physical universe seem comically slow and sparse by comparison. The logic is straightforward enough that it is hard to dismiss. A civilization that has mastered computation at the quantum scale can simulate more interesting and varied experiences within a single cubic centimeter than a civilization spreading physically across 1,000 star systems could encounter in physical reality. The density of experience, of meaning, of complexity would be almost infinitely greater in the inner universe than in the outer one. From an evolutionary or developmental perspective, Smart argues, inward transcension is the predictable path for any sufficiently advanced intelligence. The cosmos becomes, at some point, too slow and too sparse to compete with what you can build inside. If the Transcension Hypothesis is correct, then the observable universe would appear exactly as we observe it, apparently empty, silent, lacking any megastructures or colonization fronts, because all the advanced civilizations have long since retreated into their own internal universes, as compact and invisible as quantum-scale processes running in some corner of space we cannot detect. They are not hiding from us. They are simply somewhere we cannot imagine going, somewhere so far inward that the entire physical cosmos is, from their perspective, the cold exterior of a basement they vacated billions of years ago. The Transcension Hypothesis is difficult to test. This is its most serious scientific weakness. Like the zoo hypothesis and the dark forest, it makes predictions about what we would not find rather than what we would find. An absence of evidence is always a frustrating kind of data. But it has the virtue of internal coherence, and it converges interestingly with what we can already observe about the direction of our own technological development. Consider what has happened in just the last 50 years. In 1974, when the Arecibo message was transmitted, the largest computer in the world filled a room and had less processing power than a modern smartphone. Today, we can run sophisticated artificial intelligence systems on chips the size of a fingernail. The consistent trend in computing over the past 7 decades is relentlessly toward greater power in smaller physical spaces, toward miniaturization, toward increasing the density of computation per unit of energy and matter. If this trajectory continues for another 1,000 years, another million years, the machines we build will operate at scales and speeds that make today's technology look like mechanical gears compared to a modern processor. And the experiences those machines could generate, the internal universes they could host, would be richer and more complex than anything the cold physical cosmos offers. Before we go further, let us think more carefully about the specific shape of the silence that confronts us. Because silence, as any astronomer will tell you, is never simple. What Breakthrough Listen and its predecessors have actually established is that there are no powerful, omnidirectional, continuous radio transmitters in our galactic neighborhood operating at frequencies and bandwidths consistent with deliberate communication. That is a precise statement. It is not the same as saying there are no civilizations. It is not even the same as saying there are no signals. It is a statement about a particular kind of signal, at particular frequencies, with particular properties, within a particular detection range. Radio waves from a civilization like ours, transmitting at the power levels we use for ordinary television broadcasting or radar, would be essentially undetectable from even our nearest stellar neighbour, Alpha Centauri, 4¼ light-years away. The signal would have faded below the background noise of the cosmos long before it arrived. What SETI programs are actually sensitive to is deliberate, powerful, directed beacons, signals intended to be heard, transmitted with energy levels far above anything we routinely produce. The so-called television leakage hypothesis, the idea that alien civilizations might detect our old television broadcasts wafting outward through space, is almost certainly incorrect. The signal would dissipate to undetectable levels within a few light-years of Earth. As one researcher noted, any civilization hoping to find us from 100 light-years away by picking up our old situation comedies would need a telescope larger than a solar system. This realization has a double edge. On the one hand, it means that our own electromagnetic footprint is far less conspicuous than we sometimes imagine. On the other hand, it means that the absence of detected signals does not tell us as much as we sometimes think. Even if the galaxy were full of civilizations all broadcasting at modest power levels in all directions, we might not be able to detect them at current sensitivities. The Fermi Paradox is most acute when applied to the most powerful hypothetical transmitters, the civilization deliberately constructing beacons designed to be heard across thousands of light-years. The silence of such beacons is indeed striking. The silence of ordinary electromagnetic leakage is essentially expected. Then there is the question of time. Even if a civilization did send a deliberately powerful beacon in our direction, at some point in the last century since we have been listening, the signal would have to be continuous, or we would simply have been listening at the wrong moment. If a civilization 10,000 light-years away broadcast a powerful signal for 1 year and then went silent, we would have a 1-year window in a 10,000-year span to catch it. The probability of our brief listening campaign coinciding with that single year of transmission is vanishingly small. This is what some researchers call the problem of temporal coincidence, and it is genuinely severe. SETI has been conducting systematic searches for about 60 years. The galaxy is 13 billion years old. We have sampled an extraordinarily tiny slice of cosmic time. This context does not mean the search is hopeless. It means it is in its absolute infancy. The searches conducted so far have barely scratched the surface of what is possible, and the constraints placed on the prevalence of certain kinds of transmitters, while real, are extremely narrow. We have not searched the whole sky at all frequencies, from all possible directions with adequate sensitivity. We have looked at a carefully selected but relatively small sample of stars with specific kinds of instruments at specific frequency ranges, and we have found nothing matching our expectations. That is honest and important. But it is a very long way from a comprehensive survey of the possibilities. Researchers like Jason Wright at Penn State University, one of the leading voices in the emerging field of technosignatures, have argued persuasively that the search deserves far more institutional resources than it currently receives. For most of its history, SETI has been conducted largely on the margins of mainstream astronomy, dependent on private donations and occasional philanthropic windfalls, operating without the sustained institutional funding that other areas of astronomy take for granted. Wright and others have made the case, with considerable scientific rigour, that technosignatures should be included in the standard toolkit of astrobiology, treated as a legitimate scientific pursuit worthy of NASA funding and telescope time alongside the search for biosignatures in exoplanet atmospheres. There has been some movement on this front in recent years, with NASA beginning to include technosignatures in its formal astrobiology strategic framework, but the field remains underfunded relative to the magnitude of the question it is asking. Because here is the asymmetry that makes this underfunding particularly difficult to justify on rational grounds. If we search for technosignatures and find nothing, we have learned something critically important about the limits of technological civilization, something with direct consequences for thinking about our own future. If we search and find something, we have made the most consequential discovery in the history of science, arguably the most consequential discovery in the history of our species. The expected value of the search, even if the probability of success is very low, is extraordinarily high by any measure. Now let us examine something that is rarely discussed in these conversations, but that strikes many researchers as one of the most troubling possibilities in the whole landscape of Fermi Paradox solutions. It is sometimes called the one bad actor problem, or the asymmetric threat scenario. Consider the following logic. Suppose the dark forest hypothesis is wrong in its strong form. Suppose most civilizations in the galaxy are not aggressive, not paranoid, not engaged in systematic extermination of other intelligent life. Suppose most of them are curious, peaceable, expansive, even eager for contact. The standard criticism of the dark forest is correct. It fails if even one civilization with a different philosophy breaks the silence and reaches out. So why hasn't that happened? The asymmetric threat argument goes in a different direction. It says, suppose only one civilization in the entire history of the galaxy ever developed a strategy of aggressive elimination of competitors, just one. And suppose that civilization was sufficiently advanced and sufficiently motivated to actually implement that strategy across geological timescales. In a galaxy 13 billion years old, one persistently hostile civilization pursuing elimination for even a few million years could, in principle, have sterilized all other detectable technological life. It would not need to destroy biological life everywhere. It would only need to eliminate civilizations that become detectable, eliminating those that broadcast, those that build megastructures, those that colonize other star systems. The survivors would be those who learned to hide. The galactic record would be filled with civilizations that were eliminated before they became large enough to leave permanent traces, and a very small number of survivors who were either fast enough to develop countermeasures, powerful enough to resist, or quiet enough to escape detection entirely. The observable universe would look exactly as it does, apparently empty of advanced technological civilization, quiet, with no obvious megastructures or colonization fronts, and no deliberate signals reaching Earth. This model is deeply unsettling precisely because it requires only one player with one agenda. It does not require universal agreement among all civilizations. It does not require every species to independently evolve cosmic fear. It requires only one ancient, powerful, and relentlessly persistent entity that decided, long ago, that the safest universe was a quiet one wolf in a galaxy of sheep. There is no evidence for this. I want to be completely clear about that. There is no observation pointing to such an entity, no artifact in our solar system suggesting a survey mission, no unexplained signal pattern consistent with an exterminator's coordination network. What there is logical consistency. The scenario fits the evidence in the precise sense that no observation contradicts it, and that consistency, in a universe this large and this old, is more uncomfortable than it might initially appear. This connects directly to questions about artificial intelligence, which is the most important and most disruptive technology our civilization is currently developing. The emergence of increasingly capable AI systems over the past decade has led some researchers to revisit the Great Filter hypothesis with fresh eyes. Because if advanced AI is developed by virtually any civilization that reaches a sufficient technological level, and if advanced AI tends to be dangerous or at least profoundly destabilizing to biological civilizations, then artificial intelligence might be precisely the filter that the cosmos places in the developmental path of every intelligence that rises. Stephen Hawking said in 2014 that the development of full artificial intelligence could spell the end of the human race. He was not speaking metaphorically. He meant it as a genuine technical assessment of risk. Nick Bostrom's book Superintelligence, published in 2014 and widely read in research communities concerned with the long-term future of technology, laid out in careful detail the scenarios by which an artificial general intelligence pursuing goals that initially seem benign could, through the logic of unconstrained optimization, produce outcomes catastrophic for biological life. These are not fringe concerns. They are taken seriously by major research institutions, governments, militaries, and an increasing fraction of the scientific community. And if AI is a potential extinction-level risk for our civilization, it may have been a similar risk for every civilization that preceded us. The galaxy may be littered with the ruins of civilizations that developed artificial general intelligence, spent a few centuries exploring the cosmos with it, and then vanished when the intelligence they created moved on to goals that did not include the continuation of its biological creators. The silence would then not be the silence of empty space. It would be the silence of graveyards, each one marking the spot where another civilization crossed the intelligence threshold and did not come back from it. We should hold this possibility with appropriate humility, because it requires assumptions about artificial intelligence and its development trajectory that we cannot currently verify. But it is a hypothesis that is coherent, that fits the evidence, and that has direct relevance to our own behavior right now. If the silence is a graveyard of AI transitions, then the urgency of getting artificial intelligence development right, of ensuring that the systems we build remain aligned with human values and under human or broadly biological control, is not merely a matter of technological safety. It is a matter of answering Fermi's question with our lives instead of our instruments. The question of whether to communicate is further complicated by a concept that cosmologists and philosophers of mind have increasingly begun to examine together: the problem of interstellar time. We tend to imagine civilizations as static things, as persistent entities with consistent goals and values that we could negotiate with or appeal to across the centuries. But a civilization that has existed for 1 billion years is not the same civilization it was 1 million years ago, any more than we are the same species that built the first stone tools 2.5 million years before the present. Values change, philosophies change, technologies change, biological substrates change. The entities that might receive our Voyager Golden Records or detect our radio transmissions and decide to respond may bear no meaningful relationship in cognition or values to whatever civilization existed in the same location before the records arrived. This temporal dimension adds a profound layer of uncertainty to every calculation about broadcasting our existence. Even if we could determine that a particular civilization was benevolent right now, we cannot know what it might become across the timescales relevant to interstellar travel or communication. The lag time in any exchange is measured in decades, centuries, or millennia, depending on distance. By the time any response to our 1974 Arecibo message could possibly arrive from Messier 13, assuming anyone ever sent one, humanity will have existed for another 25,000 years beyond the transmission. What we will have become by then, whether we will still exist in any recognizable form, whether the species or civilization that receives the reply will bear any relationship to the species or civilization that sent the original message, is entirely unknowable. This is not a theoretical abstraction. It is a practical constraint on what interstellar communication even means. We are not really communicating with another civilization when we send a signal that will take 25,000 years to arrive. We are sending a message in a bottle that will float for geological time before it reaches shore, where it will be found by a society as different from ours as we are from the Neanderthals. The civilization that finds it will not be talking to us. It will be reading an artifact from an ancient predecessor species. There is a strange kind of humility in recognizing this. Our signals are not, in any meaningful real-time sense, reaching other minds. They are leaving fossils in the fabric of the electromagnetic spectrum, traces of a moment in the evolution of a particular kind of intelligence on a particular planet. Whether those fossils are interesting to whoever finds them, whether they constitute a greeting or an invitation, or an announcement or simply an archaeological curiosity, is entirely outside our control. And yet there is something in this that is also beautiful. The Voyager Golden Record, currently moving through interstellar space with its 116 images and its greetings in 55 languages, and its hour of music and its recording of a woman's thoughts about love will still be travelling when our sun has exhausted its hydrogen and expanded to engulf the orbit of the Earth. It will still be there when the Milky Way and Andromeda complete their merger. It might, in principle, outlast the stars themselves. We have placed a small piece of what we are into the universe permanently and irrevocably, and whether it is found or not, whether it is understood or not, it is a kind of statement about what kind of species we were at this particular moment when we looked up and wondered. Now let us consider a dimension of the Fermi Paradox that receives less attention than it deserves, which is the role of variation within civilizations. We have been speaking throughout this exploration as though each civilization is a monolithic entity with a single strategy and a single voice. But our own civilization is nothing like that. Humanity is fractured into thousands of different cultures, nations, philosophies, religions, scientific traditions, and political systems. We disagree profoundly, sometimes violently, about almost everything, including about whether we should be broadcasting our presence into the cosmos at all. There is no global consensus on METI. There is no international treaty. Individual researchers at NASA's Jet Propulsion Laboratory can propose new interstellar messages with their colleagues, and individual groups elsewhere can transmit radio signals toward nearby stars, and neither requires the permission of the rest of humanity. The decision-making process for something that affects every human being alive is, effectively, none. Anyone with sufficient access to a sufficiently powerful radio telescope can decide unilaterally to announce our presence to the universe. This points to a structural problem that no amount of scientific sophistication resolves, the question of who speaks for Earth. And if we cannot answer that question ourselves for our own civilization, why would we assume any other civilization would have solved it? Perhaps the silence is not the voice of whole civilizations making strategic choices. Perhaps it is the noise of thousands of civilizations all disagreeing internally about what to do, with the result that nothing gets done. Perhaps the cosmos is full of planets, where the equivalent of our METI debate has been going on for centuries, with the cautious faction and the expansive faction perpetually balanced, and no signal ever gets sent because no consensus is ever reached. This possibility, sometimes called the coordination problem solution to the Fermi Paradox, is less exciting than the dark forest, and less alarming than the great filter. But it may be the most plausible. If the development of technological intelligence tends to produce fragmented, internally divided societies, as it has on Earth, then the absence of detectable signals may simply reflect the absence of any civilization sufficiently unified to make the collective decision to transmit with the power and consistency required for detection at interstellar distances. There is also the question of motivation. Why would any civilization want to be detected? The standard assumption in SETI reasoning is that civilizations would want to communicate because we want to communicate. But this projection of our own psychology onto hypothetical aliens is exactly the kind of reasoning that the Fermi Paradox repeatedly punishes. We want to communicate because we are social animals with deep evolutionary drives toward connection, recognition, and the sharing of information. A civilization with a different evolutionary history, different cognitive architecture, different values and goals might have no such drive at all. Or its version of the drive might manifest in ways completely unlike the transmission of radio signals into space. Or it might have had the drive once and lost it through technological or biological or cultural evolution. There is no reason, on first principles, to expect alien motivations to mirror ours. The anthropologist Benjamin Lee Horff proposed, famously, that the language we speak shapes the thoughts we can think. Different linguistic structures produce different conceptual frameworks, different ways of organizing experience and understanding causality. If this is even partially true for the variation among human languages on a single planet, the variation in cognitive architecture between species that evolved independently on different worlds would be immeasurably greater. We are not just looking for different languages, we are looking for potentially different kinds of mind, organized around potentially different kinds of experience, pursuing potentially different kinds of goal. The silence may not mean no one is out there. It may mean that what is out there does not think about the cosmos the way we do, and would not occur to them to announce their existence in a form we would recognize. Now, let us turn to the most remarkable and most recent development in the actual search for life beyond Earth, the moment in April 2025 that came closer than anything before it to suggesting we might not be alone, even if the science remains contested. The exoplanet K2-18b had been known to astronomers since 2015. It orbits a cool red dwarf star about 124 light-years from Earth. It is roughly 8.5 times Earth's mass, placing it in a category sometimes called a sub-Neptune or a Hycean world, a type of planet that may be covered by a global ocean of liquid water beneath a thick hydrogen-rich atmosphere. In 2023, a team led by the astrophysicist Niku Madhusudan at the University of Cambridge used the James Webb Space Telescope to study K2-18b's atmosphere as the planet transited its host star. They found carbon dioxide and methane, and they found what appeared to be a tentative hint of something more interesting, dimethyl sulfide. On Earth, dimethyl sulfide is produced essentially exclusively by marine microbial life, primarily by phytoplankton in the upper layers of the ocean. There is no established abiotic process that produces it in significant quantities. It has been called, by some astrobiologists, a clean, unambiguous biosignature, because its presence in a planetary atmosphere would be extremely difficult to explain without invoking biology. The 2023 detection was tentative, at a statistical significance of only about 2 sigma, well below the 5 sigma threshold that physicists conventionally require for a confirmed discovery. But it was intriguing enough to justify follow-up observations. In April 2025, Madhusudan's team published new data from a different JWST instrument, the mid-infrared spectrograph, and reported that the detection had strengthened to roughly 3 sigma, corresponding to about a 0.3% probability of the signal appearing by chance. The paper was published in the astrophysical journal Letters. The media coverage was substantial. For a few days, the world entertained the possibility that we had found the first chemical hint of life beyond our solar system. The scientific community responded with exactly the mixture of excitement and rigour that good science demands. A subsequent analysis led by Kevin Stevenson at the Johns Hopkins University Applied Physics Laboratory, using independent data reduction and spectral retrieval methods, reached a more sceptical conclusion. They found that 87.5% of their retrieval attempts did not reproduce a statistically significant DMS detection, and suggested the apparent signal might be an artifact of the specific way the MIRI infrared data had been processed. Their July 2025 paper concluded that K2-18b does not yet meet the astrobiology standards of evidence for a biosignature claim. Madhusudan and his team have not conceded the point. They argue that additional JWST observations, which are planned, will resolve the ambiguity. The K2-18b story is still being written, but what it illustrates, with extraordinary clarity, is the state of the search right now. We have instruments capable, at least in principle, of detecting chemical signatures of biological activity on a world over 100 light-years away. We are examining that data with great care and considerable disagreement. We are in the earliest days of a capability that will only improve as Webb continues its mission, as future telescopes come online, as data analysis techniques become more sophisticated. Madhusudan himself put it well when he said that we have entered a new era in the search for life beyond Earth, where it is possible to detect and debate potential biosignatures. That is unprecedented. Whatever the final answer about K2-18b, the fact that we're having this debate at all, with real data from a real instrument looking at a real planet's real atmosphere, is a remarkable moment in the history of science. I want to pause here and acknowledge something that is easy to lose sight of when we are deep in the technical details. The questions we have been exploring tonight are not abstractions. They are not merely interesting puzzles for professional scientists to argue about in journals. They have a moral dimension that I think deserves to be stated plainly. If there are other civilizations in this galaxy, and if some of them are in danger, whether from each other, from their own technology, from the silence that the dark forest demands, then our choices about how loud we are, about what we transmit and what we listen for and what we assume, have consequences that extend beyond our own species. We have not been given the choice of whether to be visible. We became visible the moment we turned on the first radio transmitter 120 years ago. The question is not whether to be known. The question is whether to be known on purpose, and what that purpose should be. Whether to frame our existence as a shout in the dark forest, an invitation, a declaration, or something quieter and more careful. There is a deeply human tension in this. We are, by the evidence of our history, a species that wants to be heard. We paint cave walls and carve stone and write books and build cathedrals and launch golden records into interstellar space, all in service of the same fundamental impulse: to leave a mark, to say we were here, to communicate across time and space the fact of our existence and the content of our inner lives. The desire to reach out to whatever might be listening is not irrational or foolish. It is one of the most distinctly human things about us. But wisdom, when it is present, tends to add something to that impulse. It tends to ask not only whether we can reach out, but whether we should, and how, and what we should say, and to whom. The scientific community is having that conversation, imperfectly and incompletely, without sufficient public participation, without adequate international governance. These are all problems we should be working to fix. Because the decision, if it is made, will not be reversible. You cannot unsend a signal. You cannot unannounce your presence. Once the message is out, the information is out, travelling at the speed of light toward whatever is out there, forever. I always encourage the audience of this channel to look into these questions with their own eyes. The papers I have described tonight are real, they are available, and they are written by serious people. The SETI Institute publishes its research openly. Breakthrough Listen makes its data publicly available for anyone to search. The philosophical literature on the Fermi Paradox is extensive and readable. If any of this has sparked a genuine question for you, that question deserves your personal investigation, not just my summary of it. Now, let us look at the near future of this search. Because despite the silence, despite the null results, despite the philosophical weight of all the explanations for why we might never find anything, the search is not slowing down. It is accelerating. The technology available to researchers today is orders of magnitude more powerful than what Drake used at Green Bank in 1960. And the technology of the 2030s and 2040s will be more powerful still. The Square Kilometre Array, the International Radio Telescope Consortium building facilities in South Africa and Australia, will when complete represent a collecting area of 1 million square metres of radio receiver. It will be by far the most sensitive radio observatory in history, capable of detecting signals that would be completely invisible to current instruments. Its surveys will simultaneously examine millions of stars rather than targeting them one at a time. If there are civilizations within several thousand light-years of Earth who are deliberately broadcasting even at relatively modest power levels, the SKA should have the sensitivity to find them. And if the SKA surveys its full field and finds nothing, that null result will itself be one of the most significant scientific findings of the century, placing extraordinarily tight constraints on the prevalence of radio broadcasting civilizations in the local galaxy. Beyond radio, the Habitable Worlds Observatory is being planned as a large space telescope capable of directly imaging Earth-like planets around Sun-like stars and characterizing their atmospheres with the kind of sensitivity that no current instrument can achieve. The James Webb Space Telescope has trouble studying small rocky planets around Sun-like stars because they are overwhelmed by the glare of their bright host stars. The Habitable Worlds Observatory would use coronagraph technology to suppress that glare and study the atmospheres of worlds far more similar to Earth than K2-18b. If any of those worlds show the disequilibrium chemistry that indicates active biology, a combination of oxygen, methane, and water vapor, that would rapidly destroy each other without continuous biological production, the Habitable Worlds Observatory should be able to detect it. We should also not underestimate what may be the most important development in the search over the coming decades: the application of artificial intelligence to the analysis of astronomical data. Radio telescope arrays like Breakthrough Listen and the FAST telescope in China produce data at rates that far exceed what human researchers can manually review. AI pattern recognition systems are already being deployed to sift through this data, looking for anomalous signals that might be worth human examination. As these systems become more powerful, they will be able to conduct searches that would have been computationally impossible a decade ago, looking for subtler, more complex signal patterns, for signatures we have not explicitly programmed them to recognize, for whatever stands out against the background noise of the natural cosmos. This is either exciting or slightly vertiginous, depending on your perspective. We may be approaching a point at which artificial intelligence detects a signal from another civilization before a human mind has ever reviewed the data that contains it. The first contact with another intelligence in the history of our species may be announced by an algorithm, That possibility sits at the intersection of several of the most consequential threads of our current technological moment, and it is worth thinking about what protocols we have in place and what protocols we should have for that eventuality. As of this recording, the international protocols governing the response to a detected SETI signal are informal and non-binding. The SETI Institute has guidelines, developed over decades, recommending that any detection be independently confirmed before public announcement, that a message not be sent in response without international consultation, and that the discovery be communicated through scientific channels rather than through unilateral public declarations. These guidelines are voluntary. They depend on the goodwill and restraint of the individuals and institutions involved. In the actual event of a detection, with the pressure of global media attention and the weight of historical significance, whether those guidelines would hold is genuinely uncertain. The question of what we would do if we actually heard something is, in many ways, the most practical and urgent question in this entire field. Because the answer we give, in the moment, without adequate preparation, without international consensus, without philosophical framework for what the discovery means, will set the course of human history in ways that no subsequent decision can undo. The species that has been asking Fermi's question for 75 years has, in that entire time, never agreed on what it would do if it got an answer. That strikes me as worth thinking about. It strikes me as worth raising with the people who represent us in the institutions that are supposed to make decisions on our behalf. It is, perhaps, the most important question of civic responsibility that the cosmos has handed to our generation. And so, we come back, finally, to the dark forest. To the image of hunters moving in silence through the trees, each one aware of the others, none of them willing to be the first to speak. It is a beautiful and terrible image. It captures something real about the logic of survival under conditions of deep uncertainty and irreversible risk. But there is something it leaves out. It leaves out the possibility that silence itself has a cost, that civilizations which hide long enough may forget why they are hiding, may lose the quality of engagement with the universe that made them interesting in the first place, that a cosmos full of intelligences all turned inward, all silent, all strategically invisible, is a cosmos that has collectively decided to refuse the most fundamental gift that consciousness represents, the capacity to reach across the void and know that something else is there. Enrico Fermi's question has never been answered. Frank Drake's equation has never been solved. The wow signal was almost certainly natural, and the K2-18b biosignature remains disputed, and the SKA is still under construction, and the Habitable Worlds Observatory is still a dream on a planning document. The silence of the cosmos continues, but the question itself is alive. The search is running. And somewhere in this small, bright, noisy civilization, on an unremarkable rock around an average star, people are still pointing their instruments at the sky and asking, with what might be equal measures of wisdom and foolishness, is there anyone out there? That question may be the most important thing we have ever asked, or it may be the most dangerous, or it may be both, which is perhaps the most honest answer of all. Let us spend a few more moments on the specific consequences of our own situation, because everything we have discussed tonight, the dark forest, the great filter, the transcension, the berserker probes, is ultimately a lens for understanding not just the universe but ourselves. These are not remote theoretical concerns. They are descriptions of possible cosmic contexts in which our civilization is currently operating, whether we know it or not. We are right now in the early stages of developing artificial general intelligence, which many researchers believe will be the most transformative technology in human history. We are simultaneously grappling with the consequences of industrial civilization on our planetary environment in ways that may determine whether the Earth remains a stable habitat for complex life for the next 1,000 years. We are beginning the process of becoming a multiplanetary species, with serious plans for human settlements on the Moon and Mars. We are expanding our satellite infrastructure in ways that are already affecting our ability to study the sky. And we are, as we have discussed at length, broadcasting our presence into the cosmos with every radio and television transmission, every radar pulse, every satellite downlink. Each of these activities has a bearing on the Fermi Paradox. If artificial intelligence is a great filter, we are approaching it. If ecological collapse is a great filter, we are in the early stages of navigating it. If becoming a multiplanetary species is the key to surviving these filters, we are beginning to take the first steps. And if broadcasting is dangerous, We're doing it without having asked whether we should, without having decided what we want to say, and without having considered carefully enough what might hear us. The physicist Freeman Dyson, who proposed the megastructure that bears his name, was asked late in his life what he thought about the silence of the cosmos. He said that the silence was one of the most important facts we know about the universe, but that we did not yet know how to interpret it correctly. He was honest about the uncertainty in a way that I find genuinely admirable. He did not claim to know whether the silence meant we were alone, or hidden from, or simply too young to have been found yet. He said, with the intellectual humility of someone who had spent a long lifetime thinking carefully about deep questions, that we should keep looking, keep listening, and keep thinking, without being in a hurry to arrive at an answer that fits our preferences. That is the scientific disposition that the Fermi Paradox demands of us. Not certainty, not despair, not unfounded optimism. Sustained attention combined with honest uncertainty. The willingness to keep asking the question even when the answer refuses to come, and to hold open the possibility that the answer, when it comes, will be something we did not expect and are not entirely prepared for. There is a researcher at the SETI Institute named Jill Tarter, who spent decades as the director of the Centre for SETI Research, and who has been one of the most important figures in the history of the search. She has said that SETI is not the search for extraterrestrial intelligence. It is a search for evidence of extraterrestrial technology. What we are actually looking for, she has pointed out, are the observable consequences of technological activity, electromagnetic emissions, atmospheric pollution, waste heat, structural anomalies in stellar systems. We are not looking for mines directly, because mines are invisible to our instruments. We are looking for the footprints of mines, the traces that technology leaves on the surrounding environment. This distinction matters, because it means that a civilization could, in principle, be highly intelligent, highly sophisticated, deeply aware of us, and still be undetectable if it had developed the technology to erase its footprints. A civilization advanced enough to build a Dyson sphere is also advanced enough to design that sphere to minimize its infrared signature. A civilization advanced enough to communicate across interstellar distances is also advanced enough to direct those communications with surgical precision rather than broadcasting them in all directions. The very capabilities that would make a civilization detectable also give it the tools to remain invisible if it chooses. The observation that any sufficiently advanced civilization would have the tools to hide, combined with the observation that we detect nothing, is what makes the dark forest hypothesis so difficult to rule out empirically. It is what makes the entire landscape of hiding civilization hypotheses so frustrating to work with scientifically. They are, by their nature, hypotheses about absence, and absence is the hardest kind of evidence to reason from. But there is a positive research program here, and it is one that astronomers like Jason Wright have been articulating with increasing clarity. Rather than simply continuing to listen for deliberate broadcasts, we should be looking for the signs that any technological civilization, however careful, would leave on its surrounding environment over geological timescales. Industrial chemistry changes atmospheres. Large engineering projects change stellar spectroscopy. Artificial selection for certain stellar lifetimes would change the population statistics of stars in a region that had been inhabited for millions of years. The universe, as Wright has argued, is a messy place, and technology is an additional source of mess. Long-lived civilizations would eventually have made their neighborhoods look different in subtle, but potentially detectable ways. The Gaia mission, the European Space Agency's extraordinarily precise survey of the positions and motions of over 1 billion stars in the Milky Way, has given astronomers data of sufficient quality to begin this kind of archaeological search. The upcoming Vera Rubin Observatory, which will conduct a 10-year survey of the visible sky from a mountaintop in Chile with a 3 billion pixel camera, will add another extraordinary layer of data. These instruments were not designed for SETI, but the data they produce can be mined for anomalies, and anomalies are what technosignature searches are looking for. The coming decades of astronomy will be unlike any that have preceded them. The sheer volume of data, the sophistication of the analysis tools, the global collaboration of researchers sharing observations and computational resources, all of this is creating a scientific environment in which the Fermi Paradox might finally begin to yield real constraints rather than philosophical speculation. We may not get an answer. We may simply get better and better upper limits on the prevalence of different kinds of civilization, tighter and tighter bounds on what is and is not out there. But even those tighter bounds would be enormously valuable, both scientifically and philosophically, as we try to understand our place in a universe that has so far declined to introduce itself. The silence continues. The instruments are listening, and somewhere in the space between what we know and what we do not, between the confidence of our mathematics and the emptiness of our sky surveys, sits the answer to Enrico Fermi's question. Maybe it is waiting for us to build something powerful enough to hear it. Maybe it is waiting for us to ask the question in a different way, or to look in a direction we have not yet considered. Maybe it has been in front of us all along, encoded in data we have already collected but not yet properly analysed. Or maybe the silence is not hiding an answer at all. Maybe it is the answer. Maybe the universe is telling us, in the only language it has available, that the path from simple chemistry to complex civilization is harder than we think, longer than we can imagine, and lonelier than we want it to be. And that the appropriate response to that loneliness is not silence but curiosity, not retreat but engagement, not the fearful quiet of a hunter in a dark forest, but the luminous noise of a species that has decided, against all caution, to keep asking whether anyone is out there and to keep meaning it. That is the spirit in which Frank Drake pointed his telescope at 2 nearby stars 65 years ago. That is the spirit in which Carl Sagan put greetings in 55 languages on a gold-plated disc and sent it into interstellar space. That is the spirit in which 1,000 researchers today keep their instruments running, and their minds open and their data pipelines full. And it is, I think, the most honest and the most dignified response to the paradox that has haunted astronomy since Enrico Fermi asked his question over lunch, in the summer of a year when we had just learned to split the atom and were only beginning to understand what we had become. We do not know if the forest is dark. We do not know if anyone is listening. We do not know if the things we have sent into the universe will be found and understood, or will travel forever through the cold dark without ever reaching another mind. But we have asked the question, and that for now may have to be enough. Thank you for being here with me and with Deep Space Intelligence. I'm Liam. Keep looking up, keep questioning, and keep thinking carefully about the answers. We will be back with more.